Hello everyone. We're solving statics problems. Our topic, two-dimensional force systems. Our question, calculate the moment of a 1,200 newtons force about point B. Yes, a 1,200 newtons force is applied to the end of a rope. The slope of the force is given in the ratio of 1 to 2. A right triangle with a 1 to 2 ratio of its legs. We will find the moment of a 1,200 newtons force about point B. As can be seen in the figure, a moment is in the counterclockwise direction. We will find the magnitude of this moment. There are alternative ways to find the magnitude of this moment. I will find the magnitude of this moment in 6 different ways. First, let's find it in the way I think is most practical. I will move it to point C. I will apply it to point C. Of course, we remember that when we move a force from its own line of action to another line of action, we need to add a couple to the system. We will add a couple moment m to the system. So how much is this moment? What is the magnitude of this moment? The magnitude of this moment is equal to the moment of the force about point C. The moment of force T, when on the old line of action, is in the same direction and has the same magnitude as the moment of force T about a point on the new line of action. The moment of force T about point C is equal to T times the radius. The radius is perpendicular to the tangent because the T force is tangent to the pulley. The T force is 1,200 newtons. The radius is 200 millimeters. If we multiply 1,200 newtons by 200 millimeters, we get a moment of 240 newton meters. So what? The moment of the couple that we will add to the system will be 240 newton meters. This system replaces the 1,200 newtons force that was applied previously. It has the same effect. Now, we will find the moment of this system, a system consisting of a force and a couple about point B. I will find the moment of the force by resolving it into 2 rectangular components at its location. I will use Varignon's theorem. The moment of a resultant about a point is equal to the sum of the moments of the components about that point. The moment arms are known, 600 millimeters, 500 millimeters. I can easily find and add the moments of these forces. Let's not forget the force couple. We'll add them too. When we add them all, we get 1,098.65 newton meters. It's possible to solve this problem this way. This is the first method. Let's move on to the other alternatives. We can find the moment of the force relative to point B using the equation F times D. But how do we find the distance D? I recommend pausing the video and thinking about this. Think about how I can find the distance D. Let's move on. To find the distance D, let's create the following geometry. The ratio of the perpendicular sides of the resulting right triangles is always 1 to 2. I called the sides of one of the right triangles k, 2k, square root 5k, and the sides of the other, n, 2n, square root 5n. We need to find these k and n. To find the moment arm, we first need to find these. It's already clear that 2k is 500 millimeters. Therefore, k is 250 millimeters. Let's move on. Let's find n. The distance AC is 600 millimeters. It is equal to the sum of square root 5n and k. The sum of square root 5n and k is 600 millimeters. We found k to be 250 millimeters. We substitute this in and find n. So, we found k, we found n. Let's find d. What is d equal to? Square root 5k plus n plus 200 millimeters. We substitute this in and find d. We multiply by the force, find the moment from the relation F times d. We find the same moment. Let's move on. Another alternative. We can shift the force along the line of action, resolve it into 2 rectangular components at the intersection of the vertical line passing through point C, and add their moments. However, Point D isn't located on the pulley. It passes a little higher. We shouldn't neglect the small distance there. Distance CD isn't equal to the pulley's radius. Now let's find distance CD. To find distance CD, we construct right triangle CED. The ratio of the legs of this right triangle is again 1 to 2. The length of 2K is 200 millimeters. It is equal to the radius of the pulley. We need to find square root 5K. K is found as 100 millimeters. Substitute. Square root 5 times 100 millimeters gives the distance CD. Now we can calculate the moment. The moment arm of the vertical component is 600 millimeters. The moment arm of the horizontal component is CD plus 500 millimeters. The distance CD is also square root 5K. K is also 100 millimeters. We substitute all the values into the relation and find the result. Again, we obtain the same value, 1098.65 Newton meters. Another alternative, we can shift the force to the horizontal line passing through point C and resolve it into two rectangular components there. This time, we need to find the distance CD. When finding the moment arm of the vertical component, we need to find the distance CD. Again, the resulting triangle's vertical sides are in the ratio of 1 to 2 a triangle. I call them K, 2K, square root 5K. The distance K is equal to the radius. So, 200 millimeters, square root 5K is the length we need. We'll write 200 millimeters instead of K and find the moment. The moment arm of both components is now known. The moment arm of the horizontal component is 500 millimeters, and the moment arm of the vertical component is square root 5K plus 600 millimeters. From here, we get the same result, 1098.65 Newton meters. Another alternative. We can shift the force to the same horizontal as point B and resolve it into two vertical components there. Therefore, the horizontal component does not create a moment. Only the vertical component has a moment. We need to find the moment arm of the vertical component. We need to find the distance BD. I recommend that you think about how to find this distance, and again, pause the video and think about it. Let's move on. We're creating this geometry. The resulting right triangles here, again, have vertical sides in the ratio of 1 to 2. The height of the large right triangle is 500 millimeters. So, the base is 1000 millimeters. It seems obvious. Let's call the sides of the small right triangle K, 2K, and square root 5K. The distance K is equal to the radius, which is 200 millimeters. So, no problem. We found the length we were looking for, square root 5K. We'll write 200 millimeters instead of K. Since the horizontal component passes through B, it doesn't create a moment. The moment arm of the vertical component is square root 5K plus 1000 millimeters plus 600 millimeters. We find the moment by performing the necessary calculations. We find the same value. Finally, we shift the force along the line of action, so this time, the vertical component passes through point B. This time, the vertical component doesn't create a moment. Only the horizontal component has a moment. If we find the moment of the horizontal component, we will find the moment of 1200 newtons. The moment arm of the horizontal component is the distance BD, the length we're looking for. Let's find the distance BD. AB is given as 500 millimeters. Therefore, we'll find AD. Let's find AD. The geometry we created yielded two right triangles. Again, the ratios of the right sides in right triangles are 1 to 2. In a right triangle with base AC, the height is 300 millimeters. Because the distance AC is 600 millimeters. If the base is 600 millimeters, then the height is 300 millimeters. In the other, smaller, right triangle, the larger side is equal to a radius of 200 millimeters. Therefore, the smaller side is half that length, 100 millimeters. The side we need to find is square root 5K. We substitute 100 millimeters for K. We find square root 5K, the length we're looking for. The moment arm of the horizontal component is square root 5K plus 300 millimeters plus 500 millimeters. We perform the necessary calculations and we get the same result again. MB equals 1098.65 Newton meters. A moment in the counterclockwise direction. Goodbye.